Okay, so this is the final linear program of this chapter, and this is like a more complicated multi-period linear program. So I'm not going to kind of try and build this one from scratch. I'm just going to go through the model given by the book and then just kind of show you how to optimize it in Solver. So the idea here is we have $200,000 that we want to invest throughout 6 periods. And we basically have a set of investments. Investment in A kind of returns 0.25% in the next period. Investment B kind of returns 1% 3 periods later. And investment C returns 2.3% 6 periods later. So there's the idea that we have these, it's almost like, fixed interest and fixed term kind of money market deposits. And we have a little diagram here that says how it works. So if you invest like $10,000 in A, you would get like you would get 10,250 back in 2, and then you could invest that again. Now, we actually have some kind of idea here of the returns. So we actually put these returns into a specific spreadsheet. So let's imagine that we don't have anything in here. We have no investments. Now imagine that I invest $10,000 in A in period 1. We'd get this return of 10,025 in period 2. I invest $10,000 in B in period 1. I get 10,100 in period 3. And if I invest 10,000 in C, then I get 10,232.3% in period 7. Now notice that these cells are blank. And that's simply because, if you invest in period 1, you can't get a return in period 1. And period 1 is the first period you can invest in. For B, you can't get it. If you invest in B in period 1, you can't actually get a return for 3 periods. So we're going to have no returns before period 4. And again, in C, we don't get any return in C until period 7, like add 6 periods. So again, we're not going to get any return here. And the return is just the amount we invest multiplied by this rate of return. So here, H14 is like, so we have $10,000 and we multiply it by 1 point, and that's 0.25%, so it'd be 1.0025 in order to get the return. So we have the investments and we have returns. Now we have a series of constraints. We've got our $200,000, but, we actually need to spend maybe we need to spend some money. So this is the amount we need to spend in each of these following 6 months. So the first month, we're obviously blowing it on something, a fancy car or something. So we spent $50,000. Month 2, we actually earn more than we spend, so we get back $12,000. We spend a net of $23,000 in period 3. And we get back $20,000 in period 4. So it's like fluctuating expenses. And at the end of each period, we're required to have $10,000 in cash. So we actually, in the first period, so we have to actually invest to get our $10,000 in cash. We spend $50,000. So that gives us $150,000. So we need to spend $140,000 to get our $10,000 in cash. So this is the hard constraint that we have $10,000 at the end of each period. So let's remove this. Now, we also have this idea, and this is where we get the balance at the end. So these balances at the end of the periods need to be $10,000. And the balance here, again, this is the amount available minus our net expenditures minus the amount we invested. So if we'd gone and invested, you see at the moment it's 150,000. So if we'd gone and invested, say 140,000, we'll see we're now at the correct balance. So the idea, and this kind of follows through. So the balance here is, we have the balance here, and then this is basically the new amount available is our previous balance plus any returns on investment, which gets us to here. Again, subtract from expenditures and amount invested. So we just have this balance kind of going all the way to the end. And basically what we're trying to maximize is our returns at the end, the last period returns. And all of our investments need to kind of come to fruition in period 7. So for example, we can't invest a load of money in C in period 6. That wouldn't make any sense because we don't get that money back. We're actually losing. We're losing on that. But we don't kind of explicitly model that. So the main thing is we have all these balance constraints, what I just described is in the mathematical program, and we're just maximizing our return at the end. And basically, we want to keep these balance constraints to be $10,000. So let's go to Solver. So we're maximizing our return, which is here in H23, by changing these variable cells, subject to the constraints. Whoop, what's something went wrong there? Oh, I think I doubled the H or something. So by changing these investment amounts, subject to the constraints that all these are equal, or in fact, looking at the to $10,000. Let's click OK, and let's click Solve. We're going to use the simplex. And we get 123,919, which is what we got on the book supplied. So you can see here that we're investing in period 1. We have to invest $140,000. We invest 31,000 here and 108,000 in C, which kind of comes of age in period 7, and we get that money plus 2.3% back. The next period we invest about $40,000. We don't invest anything in kind of period 3, but then we invest a little bit more in period 4. And then in period 6, we don't invest. If you think about period 3, we don't invest any money because basically we have additional expenditures which take away all of our money. Now, just for interest, let's relax this a little bit, and let's do, as per the linear program, let's do greater than equal to as our constraint. And we get exactly the same value. So I just I did it as equal to $10,000, but greater or equal to $10,000, simply because if we have additional cash beyond what's required, we're not using that cash. We're not actually using it to invest. If we had, say, we had $10,001, we could have put that $1 in investment A and got it back in the next period at $1. $1.0025. So if we have additional money than required, we can always get a better return by putting in investment A. That's why our equals running it with an equals constraint and a greater or equal constraint gives us exactly the same result.